Okay, hello everyone and welcome to my data mining project demonstration. In this demonstration, I will walk you through the entire process of analyzing, cleaning, balancing and training a machine learning model on real-world attack data from the Middle East and North Africa region. So this project is designed to help classify different attack groups based on some various features. And I hope by the end of this demonstration you will have a clear understanding of how the data is processed, how imbalances in classification problems are handled, and how a machine learning model can be trained to make predictions. So let's get started. The first and most important step in any data mining or machine learning project is understanding the data set. If we don't understand the data, we can't extract meaningful insights or build an effective model. In this project, we are working with a data set that contains information about terrorist attacks in different regions. But since we are particularly interested in studying attacks in the MENA region, which is Middle East and North Africa region, the first thing we do is to filter out all the other regions and focus only on the MENA region data. The dataset contains many columns, but not all of them are useful for our purpose. Instead of working with every column, we carefully select only the ones that provide valuable information for classification. So these include the country and province or the states where the attack took place, the type of the attack, such as bombing or assassination or hostage situations, the number of people killed or wounded, which helps measure the severity of the attack, the group responsible for the attack, which is what we are trying to predict, the type of the target that was attacked, such as civilians or government buildings or military, etc., the year and month when the attack happened, whether the attack was successful or not, whether it was a suicide attack or not, or whether the attacker was an individual or part of a larger group. So these features are crucial because they help us understand different patterns in the data and build a model that can predict which group might be responsible for an attack based on these attributes. And we pick these attributes because these attributes are the first attributes that can be collected when a recent attack happens, so we can quickly get the data and make a prediction. So the next phase is cleaning and pre-processing the data. So raw data is rarely perfect. In real-world scenarios like this, datasets often contain missing values, inconsistencies, and many errors. So cleaning and pre-processing are critical steps to ensure that the data we work on is structured properly for machine learning operations. One of the first things we do is handle missing values. Many of the numerical columns, such as the number of people killed or wounded, have missing values in the dataset. And we assume that missing values in these columns likely mean 0 casualties, so we fill them with 0. Next, we create a new severity column by adding the number of people killed and wounded together. This column gives us a single metric that represents how severe the attack was. After this, we can drop the original columns for killed and wounded because they are now redundant. Another important step is filtering out rare classes. Some terrorist groups are responsible for only a handful of attacks in the dataset. So if a class has too few samples, the model won't have enough examples to learn from, which leads to poor performance. So to solve this, we remove groups that appear in fewer than 30 attacks, and this ensures that we are working only with meaningful classifications. And for this phase, finally, we need to encode categorical data. Since machine learning models require numerical inputs, we convert all categorical variables such as country names, attack types, target types, and other stuff into numerical values using label encoding. And this process assigns a unique integer to each category while preserving the original meaning of them. So next, one of the biggest challenges in classification problems and also in my project is imbalanced data. This means that some classes have far more samples than others, and if left unsolved, this imbalance can cause the machine learning model to be biased toward the dominant classes, which ultimately leads to poor predictions for the minority classes. And in this project, each class is equally important, so we need to solve this. To solve this, I implemented a custom balancing function that either removes excess samples from majority classes or adds new synthetic samples to minority classes. So here's how it works basically. For classes that have more than a set of number of samples, I set this to 500. We randomly remove extra samples to balance them. And for classes that have fewer than 500 samples, we duplicate existing samples to bring them up to the required level, which is 500. And if a class already has 500 samples, we leave it unchanged. So this process ensures that all classes have an equal number of examples, and by that allowing the model to learn from each class with minimal bias. Once the balancing process is complete, we visualize the class distribution before and after balancing using bar plots. This helps us confirm the dataset is now balanced and ready for training. So after pre-processing the data, the next step is to split it into training and test sets. The training set is used to train the machine learning model, while the test set is used to evaluate how well the model performs on unseen data. I used an 80 to 20 split, meaning that 80% of the data is used for training and 20% is reserved for test purposes. And this ensures that the model learns from the most of the data set while having a little portion for evaluation purposes. So splitting the data properly is important because training the model on all the data without testing would make it difficult to measure, and without measuring it we cannot improve it, so it's important. So ultimately, the training process. For this project, I used the random forest classifier, which is a powerful and widely used machine learning algorithm for classification tasks. Random forest works by creating multiple decision trees and averaging their results, so making it kind of prone to overfitting. So we set up the classifier with the best parameters, 100 decision trees for better performance and a maximum depth of 30 to prevent overfitting. These parameters are gotten through another program. I ran it for a few hours. I tried all of them, performed the parameter optimization and got these as the best parameters. No bootstrapping means the model does not use random sampling. After defining the model, we train it using the balanced training data. Training a machine learning model involves feeding it the input features and the corresponding labels so that it can learn patterns and relationships in the data between the features and labels. Once training is complete, the model is ready to make predictions on the new data. So, to evaluate how well the model performs, I used multiple metrics. Firstly, accuracy. It is the percentage of correctly classified cases. Then precision, the proportion of positive identifications that were actually correct. Then recall, the proportion of actual positives that were correctly identified. This one is very important and it's my main metric. And lastly, F1 score, which is a balance between precision and recall. We calculate these scores to see how effective our model is in predicting attack groups. Additionally, we generate a classification report which provides detailed performance metrics for each class. If we find that certain classes are performing poorly with an F1 score below 0.5, we identify them as underperforming classes and we can further investigate the potential improvements. So to make our findings clearer, we also create some visualizations. First one is feature importance plot. This shows which input features had the most influence on the model's predictions. Second is confusion matrix. It's a heat map that shows how many predictions were correct and where mistakes were made. So these visualizations provide insights into how well the model is working and highlight areas where improvements might be needed. So thank you for watching, and I hope this demonstration helped you understand the full process of building a classification model in a data mining project. So let me run it. These are class counts before balancing, and this is class counts after balancing. And this is the feature importance graph, as you can see. And it's okay. And this is the confusion matrix. It being diagonal means the model performs okay. And so there are tiny problems, but it's alright. And as you can see, we get no underperforming classes. Here are the current scores.